Hello, very good morning. We are going to continue on with the final part of the video for chapter 4, where previously we stopped at the introductions toward the summary or summarize of the reaction of the period 3 elements with the oxygens. So we are going to finish off everything, including the discussion in details for all the reactions in between the period 3 elements with oxygen and their acid-base characteristic. Okay, shall we begin? All right, so we are going to first up with a reaction between sodium and oxygen. Now, sodium is a grayish silvery solid that is kept in a paraffin oil to prevent the oxidation of the metals. So when exposed to air, a whitish layer of the sodium peroxide is formed according to the equation 4Na plus O2 give 2Na2O. When the oxide is further heated, so it turns to pale yellow color, which is actually a sodium peroxide. According to the equation, 2Na2 plus O2 give 2Na2O2, okay? And both sodium peroxides and sodium oxides dissolve in water to form sodium hydroxide and some side product, okay? So if sodium peroxide dissolve in water, so you form sodium hydroxide and hydrogen peroxide. If sodium oxide dissolve in water, you form sodium hydroxide. Okay, and by the way, all these equations you need to memorize if you are not good in balancing. So, yeah, okay. Now, we say that sodium oxide is a basic oxide because it can react with hydrochloric acid to produce salt and water. So, the equation is Na2O plus 2HCl give 2NaCl plus H2O, where the ionic equation is Na2O plus 2H plus give Na2 plus H2O, right? Okay, so this is for the reaction of sodium, okay, with oxygens. Okay, then we have magnesium with oxygen. So the reaction of magnesium oxygen can speed up by heating, where according to the equation, 2Mg plus O2 give MgO. So at the same time, magnesium also burn in air, which also contain nitrogen to form nitrogen magnesium nitride, which is a yellowish solid. According to the equation, 3Mg plus N2 give Mg3N2. Okay. However, unlike sodium oxide, magnesium oxide does not dissolve easily in water to give a hydroxide solution. So it still react, but it will react mostly with steam. So where magnesium oxide will form magnesium hydroxide easily. Okay. So magnesium oxide can also show basic properties when react with the acid. Okay, where according to the equation, MgO plus 2HCl give MgCl2 plus H2O, or in the form of ionic equation, MgO plus 2H plus give Mg2 plus H2O. Okay, all right, so this is for the magnesium. All right, and then we have for aluminium. So aluminium, even though aluminium is the least negative among all three, aluminium react passively with oxygens since aluminium, by its nature, is coated by an impervious oxide layer. However, if the layer is removed, aluminium is ready to react with oxygen to form aluminium oxide, according to the equation, 4Al plus 3O2 give A2Al2O3. So aluminum oxide is an M4 ferric oxide because it can react with acid as well as a base. Okay. Why is it like that? Because aluminum oxide is an ionic compound with high covalent characteristic due to the fact that aluminum ion has a high covalent characteristic due to its small ionic radius and the high charge that give a high charge density, hence high polarizing power. So the equation given for the reaction between aluminum oxide and acid is Al2O3 plus 6HCl give 2Al2CO3 plus 3H2O in the form of ionic Al2O3 plus 6H plus give 2Al3 plus 3H2O. Whereas when we react with base, Al2O3 plus 2NaOH plus 3H2O give 2NaLOH4. Ionic, we have Al2O3 plus 2OH minus plus 3H2O give 2ALOH4 minus here. Okay, so that is for the reaction between aluminium and also oxygens. Okay. Okay. Then we have reaction of silicon with oxygen. So silicon are whole by giant covalent structure. Therefore, in order for silicon to react with oxygen, you require a very high temperature to break. Only then silicon will react with the oxygens according to the equation. Okay, and for information, silicon dioxide does not dissolve in water as it has a giant covalent structure. But SiO2 can react. It's an acidic oxide because it can react with hot concentrated sodium hydroxide. Okay, hot concentrated alkali. These are very important conditions. According to the equation, SiO2 plus 2 NaOH give Na2SO3 plus H2O here. So in the form of ionic, SiO2 plus 2OH minus give SiO3 2 minus plus H2O. Okay, so this is the reaction of silicon with oxygens. Then we have the reaction between phosphorus and oxygen. So unlike all these metals, so phosphorus actually possess more than one oxidation state. Okay, so where in the case of phosphorus, it will form phosphorus 3 oxide, P4O6, and then phosphorus 5 oxide, depending on the condition. So if we have under limited air, okay, under limited air, phosphorus react with oxygen to form phosphorus trioxide, P4O6, and under excess air, phosphorus react with oxygen to form P4O10 here. Okay. Now, both of these oxides are acidic and dissolve in water and are hydrolyzed to form the corresponding acid. This phosphorus trioxide, P4O6 plus 6H2O form H3PO3, which is phosphorus acid, and then the P4O10 plus 6H2O form 4H3PO4, which is a phosphoric acid. Okay. Okay, so other than dissolved in water, acidity of the phosphorus oxide can also be proven when you react with the alkali. So when P4O6 react with 12 NaOH, you form 4 Na3BO3 plus 6H2O, or in the form of ionic equation, P4O6 plus 12 OH minus give 4 PO3 minus plus 6H2O. And in P4O10, you react with 12 NaOH2 to form 4 Na3PO4 plus 6H2O. Now the ionic equation is P4O10 plus 12 OH minus form 4 PO3 4 minus plus 6H2O. Okay. So these are all the relevant equations that you have to remember. So this is the reaction of phosphorus. And then we also have sulfur. Okay. So sulfur react with oxygens with different oxidation states, which is sulfur dioxide and also sulfur trioxide. However, phosphorus dioxide is first formed before it further oxidized to become sulfur trioxide. Okay. So when sulfur is first burned with air, so S plus O2 give SO2, and then the sulfur dioxide is then further oxidized in the excess oxygen, according to the equation, 2SO2 plus O2 give 2SO3. So in our troposphere layer, SO2 that are released to the environment in the heavy vehicle and mining activity are slowly oxidized to SO3 with the aid of UV from the sunlight, and the nitrogen oxides according to the equation SO2 plus NO2 give SO3 plus NO. So the NO is the gas that forms the photochemical smoke that you see early in the morning that become hazy inside there. So these catalytic reactions we shall further discuss when we go to semester 2 later. There is a special subtopic for it. Okay. Okay, so now sulfur oxide, similar to phosphorus oxide, are hygroscopic. That means react vigorously with water. Okay, and as they are readily dissolved inside rainwater and hydrolyzed to form sulfurous acid H3PO, H2SO3, and sulfuric acid H2SO4 respectively. So when sulfur dioxide dissolved in water, SO2 plus H2O form H2SO3, whereas SO3 plus H2O form H2SO4 here. So other than dissolved in water, acidity of the sulfurous oxide can also be proven when dissolved with the react with alkaline solution. Sorry for the typing error, not acidic but alkaline basic solution. Okay, where the equation goes like this. SO2 plus 2 NaOH give Na2SO3 plus H2O, or in terms of ionic, SO2 plus 2OH minus give SO3 2 minus plus H2O. And when we add with alkali, SO3 plus 2 NaOH give Na2SO4 plus H2O, or in the form of ionic equation, SO3 plus 2OH minus give SO4 2 minus plus H2O. Now, because of these properties, so sulfur dioxide can easily act as often added to the food industry as a preservative. Why? Because it can help to prevent the growth of bacteria in the food, and it also can act as an antioxidant. Okay, it can also act as an antioxidant. Why? Because sulfur dioxide is a good reducing agent. So this is the reason why sulfur dioxide is often used in the preservative, because it can also act as an antioxidant, because SO2 can still readily to oxidize to become SO3 here. Okay, and last but not least, we have chlorine. So chlorine does not react directly with oxygen under condition. So the chlorine oxide is a yellowish gas that is made by just passing dry chlorine with the precipitate mercury 2 oxide. So all these equations actually you don't need to memorize. Just know the fact that chlorine oxide can be prepared by using alternative methods. So I just go through. Okay, so and then chlorine also have another oxidation state, which is Cl2O7 through the dehydration. So both of these are dissolved in water to form the hypochlorous acid HClO and chloric acid HClO4 according to these equations in here. Okay, so with that, that is all the chemical reactions in between the period 3. Then it formed the oxide, and then the oxide you also learn about their acid-base properties, so which we can then summarize in the following table. Okay, so in here I help you to summarize of all the reaction that we discussed just now. So on how the reaction of the period 3 oxide with water. So that is why it is important for you to write everything on your own, write it as short notes or whatsoever. Okay, so these are the equations here. Okay, so okay, I help you a little bit on this one. Okay, where sodium oxide. This one you just memorize one of them. So Na2O plus H2O give to Na2O2, magnesium oxide plus H2O. This one is reverse. This one is gas, but if it is liquid, then you should write as a reversible sign. P4O6 plus 6H2O form 4H3PO3. When we add with P4O10, we form H3PO4. Sulfur dioxide from H2SO3, sulfur trioxide from H2SO4, and then the chlorine oxide acts accordingly to the equations in here. Okay, so this is the reaction of the period 3 oxide with water. And then finally, we also have the summarized table when you react with the HCl and also NaOH here. Okay, so for the sodium oxide, so sodium oxide react with HCl to form NaCl plus H2O, where it does not react with alkali. Same goes with magnesium oxide. So magnesium oxide react with HCl to form MgCl2 plus H2O. So aluminum oxide is amphoteric, where Al2O3 plus 6HCl give to AlCl3 plus 3H2O. And then Al2O3 also react with 2 NaOH to form NaAlOH4 here. So that is why aluminum oxide is amphoteric. Some silicon dioxide react with 2 NaOH to give 2 Na2SiO3 plus H2O. So P4O6 react with 12 NaOH to form 4 H3PO3, and P4O10 react with 12 NaOH to form Na3PO4. Sulfur dioxide react with 2 NaOH to give Na2SO3, while sulfur trioxide will react to form Na2SO4. Chlorine oxide will form NaClO, and Cl2O7 form NaClO4. Yes. Okay. So I hope that all these summarized table will help you to quick revise on your equations and things, right? And for the final part of our video today, we are going to have a look at the properties of the physical properties of the oxide of period 3 elements here. So here we have the this information is obtained if you look at the previous tables, where I also apply the melting point. Okay, so this is how the graph comes by. Okay, so it can be generally categorized in three categories, where we have sodium, magnesium, aluminium is formed by ionic compound formed by giant ionic crystal lattice. Silicon dioxide is a giant covalent structure. Phosphorus, sulfur, and chlorine are simple covalent molecules formed by weak van der Waals forces. So without further ado, let's have a look one by one on how are we going to describe their properties in here. Okay, so let's start from the magnesium oxide and sodium oxide. So we call them as a simple giant covalent. So this is sorry, Na2O, MgO, and Al2O3 giant ionic crystal. These SiO2 are giant covalent. P4, 6P4, SO3, and HCl are simple covalent molecule formed by weak van der Waals forces. So let's have a look at the description one by one, starting from the magnesium oxide. So sodium oxide, magnesium oxide, aluminum oxide are giant covalent, giant ionic crystal lattice. Okay, so this is how we are going to describe them. Sodium oxide, magnesium oxide, aluminum oxides are ionic oxide formed by giant ionic crystal lattice. So melting point is influenced by the strength of the ionic bonds in there, where the strength of the ionic bonds are determined by two factors, which is the charge of both ions and also the ionic radius for both oppositely charged ions in here. So in here, it is come to nature that sodium oxide, magnesium oxide has a higher melting point compared to the sodium oxide because sodium has a smaller charge and greater cationic radius compared to magnesium ion. So that is why you have a higher charge and smaller ionic radius inside the magnesium that cause to have the ionic bond strength inside the magnesium oxide to be higher. So that is why magnesium oxide has the highest melting point. In the case of aluminium, even though the ionic charge and ionic radius of aluminium is greater than that of the magnesium oxide, I think I make a typing error in here. Sorry for that. We should say that. So aluminium 3 plus has a higher charge, smaller ionic radius. Sorry for that. So supposedly, aluminium ion has a higher strength compared to magnesium, right? However, surprisingly, the ionic bond strength of aluminum oxide is weaker than that of the magnesium oxide due to the aluminum ions has a high charge density and therefore high polarization power. As a result, aluminum oxide has a high covalent characteristic compared to magnesium oxide, hence lower the melting point of the magnesium oxide. Yeah. Okay. So that is how we are going to describe for the sodium oxide, magnesium oxide, and aluminum oxide. Okay. Then we are going to have a look at the silicon dioxide. So silicon dioxide is a giant covalent structure where each silicon is covalently bonded with four other oxygen atoms to form a giant covalent network. So they are very strong. That's why it requires high temperature to break them. Okay, and then phosphorus, sulfur, and chlorine oxide are simple covalent molecules formed by weak van der Waals forces. As the relative molecular mass increase, you should write as relative. So you have, especially when we compare, P4O10 is the highest, followed by Cl2O7, and then SO3. So the strength of the weak van der Waals forces also increase accordingly. Therefore, the melting point also increase. Okay. All right, so with that, that is all for the chapter 4 videos. So in the next lesson, we are going to continue with the chapter 5 video. All right, so with that, I end my talks for chapter 4 and have a good day. Thank you.